In this video, we're going to talk about absolute value equations and absolute value inequalities. Let's start with absolute value equations. Before solving example 1, I just want to remind you that absolute value means distance from 0, and an absolute value, because it's distance, will be a positive value. So if I have absolute value of x equals 7, we actually end up with two answers. X could be 7, because the absolute value of 7 is a 7. And x could also be negative 7, because the absolute value of negative 7 is also positive 7. So we actually have two answers for x, positive 7 or negative 7. This is the approach we're going to take, that if we isolate the absolute value, then we're going to use a positive and negative sign to show that what's inside that absolute value could be positive or negative, and then the absolute value will force it positive or 0. So let's go ahead and start with example 1. I'm going to isolate the absolute value so that we can take this shortcut of separating it into two equations, one with a positive and one with a negative. So let me move my 5 over to the right. I have 2 absolute value of 9 minus 4x equals 14. Divide both sides by 2, again trying to get that absolute value by itself and isolated. And we have 7. And just like we said over here, once we know that we have the absolute value isolated, what's inside the absolute value, 9 minus 4x, could be a 7, or 9 minus 4x could be a negative 7, and then the absolute values force that to become a positive 7. So let's solve each of these two equations that we've created. So subtract 9, divide by negative 4, and we end up with positive 1/2. And then over here, subtract 9 and divide by negative 4, and we end up with 4. Now notice this is an equation, not an inequality, no greater thans or less thans here. So we actually have two individual answers, 1/2 and 4. Another way to write that is using set brackets, that our answer is 1/2 comma 4, and these set braces mean individual points. So these are individual points on a number line. Let's take a look at example 2. What if you ended up with two absolute values? I'm actually going to go a long way and show you how there are actually 4 scenarios that could happen. So in case 1, what if I leave everything the same and make no changes? That's kind of like that first equation we made over here. Equation 1 was no changes, right? What was on the left, 9 minus 4x, stayed 9 minus 4x, and what was on the right was a 7, it stayed a 7. Equation 2 was that we multiplied one side by negative 1. And it was a quicker way for us to multiply the 7 by negative 1 to make it negative 7, and then we know that the absolute value of each side would make that become a positive 7. Same idea down here. Our first case is going to be no changes. So we're going to leave the left 3x plus 2, but no absolute value. We're going to leave the right x minus 5, again no absolute value, and we're going to solve. So I get 2x equals negative 5, and I get 2x equals negative 7. Dividing by 2, we get x equals negative 7/2. Now, case 2, or equation 2, like we did above, we're going to multiply one side by negative 1. So I'm going to choose to multiply the right-hand side by negative 1. So I'm going to keep the left-hand side as it is, and I'm going to multiply negative 1 times the entire right-hand side and distribute. So 3x plus 2 equals negative 1x, and then plus 5. And then we're going to solve. So adding 1x makes it 4x plus 2 equals 5. Moving the 2 over we get 4x equals 3, and dividing by 4, we get x equals 3/4. So we have two answers right now, -7/2 and 3/4. I'm going to show you two more cases, but what you're going to find is the next two cases are really just an alternate version of case 1 and case 2. So let me look at case 3. Case 3, I'm going to multiply one side by -1, but now I'm just going to multiply the other side. So before I chose the right-hand side to multiply by -1, this time I'm going to choose the left-hand side to multiply by -1. So -1 times 3x plus 2 equals x minus 5, and then distribute. So -3x minus 2, and then start to solve. I'm going to add the 3x. So I get -2 equals 4x minus 5, add the 5 to both sides, and we get 4x equals 3, divide by 4. Notice that we get the same answer of 3/4. These two are the same. So we actually don't need both case 2 and case 3. We're just going to choose one of them. So whether you choose to multiply the right-hand side by -1 or the left-hand side absolute value by -1, you actually end up with the same answer. Let's take a look at one more case, case 4. And case 4 is multiply both sides by -1, or both absolute value quantities by -1. So multiply both sides, and remember we've isolated the absolute values, by -1. And you're going to find that this will actually be the same as case 1. So let me multiply the left-hand side by -1 and the right-hand side by -1. And then start to solve. Let me add 3x to both sides. And that ends up being a positive 2x over here on the right. Subtract the 5. And maybe you're already starting to see there's my -7 equals 2x, divide by 2. And we get -7/2 as our x. And if we look back to where we were a minute ago, we also had the -7/2. So really case 3 and case 4 are repetitions of what we already did with case 1 and case 2. So to solve something that has two absolute values that are isolated, one on each side of the equation or of the equal sign, we really can just focus on two cases because the others are repeats. And our answers are -7/2 and +3/4 to finish that question. Let's go ahead and start taking a look at absolute values, or excuse me, absolute values with inequalities. So we just looked at solving an equation, and how we did it is we isolated the absolute value and then separated into two equations, x minus 2 equals 4 and x minus 2 equals -4, and solved from there. So here we get x equals 6. And on the second equation, we get x equals -2. Now keep in mind, because this is an equation, these are individual points. So here's -2, and here's 6, and no shading at all. They're just individual points, and how we write that for our solution is -2 is an answer and 6 is an answer. And we use those curly brackets, curly braces to indicate that they're individual points on the number line. Now, how the book is going to show you to use case 2 is that it's sandwiched between 4 and -4. So x minus 2, we're looking at 4, and then on the other side of 0, we would have a -4. So there's our +4 and -4. And then solving this 3 part inequality, we're going to end up with -2 and 6. So same two really important values on the number line. In this case, because there's just a less than sign, they're going to be open circles. And we're going to shade in between them because our x is smaller than 6 and at the same time bigger than -2. And so we would have a parenthesis because of the open circle, -2 to 6, parenthesis, and all the values in between. Okay, and so here's our interval notation, meaning we have infinite number of solutions there. Okay, an alternate way to get the same answer is how we solved inequalities previously, just without absolute values. We solved them like we would have with equal signs and got those important values on the number line and then tested each region. So if we tested a number like -5 back in the original inequality, or if we tested a number like +7 back in the original inequality, we would find that those don't work. So that's just an alternate way of solving our absolute value inequalities, similar to how we did before. Case 3, because it's greater than, you're looking at the extremes of the number line, so going out towards infinity. So one way to solve it would be x minus 2 is greater than 4, and then the second one would be or x minus 2 is less than -4. So again, looking at that +4 and -4 due to the absolute value. And then I'm going to add 2 to both sides. So x is greater than 6, or x is less than -2. So here's our -2, here's our 6. We said greater than 6, so heading this way, less than -2, so heading to the left. And so our interval notation would be -infinity to -2. And then the second part of our solution would start at 6 and go to infinity. Okay, so what I propose is that for all three of these cases, whether it's an equation or an inequality, we could solve it as if it's an equation to get those two important numbers on the number line. And then if it's a greater than or less than, or greater than or equal to and less than or equal to, test those different regions of the number line to find out what portions would need to be shaded to be included in our solution. Let's go ahead and start example 3. So I'm going to start out, and I'm going to solve this as if it were an equation. 3 absolute value of 5 minus 8x plus 6 equals 24. And one method is to make sure we isolate the absolute value before creating our two equations. So we end up with 24 minus 6 is 18. Divide both sides by 3, and we get absolute value of 5 minus 8x equals 6. Now that we have our absolute value isolated, we can then create our two different equations. So equation 1 is going to be keep everything the same, no changes in sign, no multiplications by -1. So 5 minus 8x equals 6. Our equation 2 is going to multiply one of the sides by -1, and remember how we talked about it before, it isn't going to matter which one. So probably the shortcut is to multiply 6 by -1. So we've got 5 minus 8x equals -6. Solve both equations. In one of them we get -1/8. And in the second equation, our negative over negative will become positive. We get 11/8. So let's put those on the number line. So here's -1/8, and here's 11/8. And we need to test something in each region. So maybe I'll test -1. I always like to test 0 if it's a possibility because it's usually a quick calculation. And over here, 11/8 is a little bit bigger than 1. It's actually 1 3/8. So let's maybe check something like 2. And always go back and check in our original. So here, checking with the number -1, we have 3 absolute value of 5 minus 8 times -1 plus 6. Is that bigger than 24? So inside the absolute value, we have 5 plus 8 plus 6 is greater than or equal to 24. That becomes 13. And the absolute value of 13 stays 13. Times 3 is 39. And we can kind of see from here that 39 plus 6 is going to be 45, and yes, that is bigger than 24, so we are for sure going to shade in that region. Kind of looking ahead, because of the equal line, we're going to include that -1/8, so whether you do a solid dot or you include the squared brackets. Let's go ahead and try here in the middle with 0. 5 minus 8 times 0 inside the absolute value. And then simplifying, 5 minus 0 is 5, and the absolute value of 5 stays a 5. So 5 times 3 is 15, plus 6 is 21, and is 21 bigger than or equal to 24? That one's a no. And then looking at the third part of our number line, using x equals 2 as a testing. So 3, absolute value of 5 minus 8 times 2, plus 6. Inside the absolute value, we have 5 minus 16. And then 5 minus 16 ends up being negative 11. But then taking the absolute value of negative 11 is positive 11, times 3 is 33, and 33 plus 6 is definitely more than 24, so we'll have this region to the right shaded also. And again, including the 11/8. So our final answer in interval notation would be negative infinity to negative 1/8, including negative 1/8, and then picking up again at 11/8 and going to infinity. So the reason I like this method is we don't have to remember whether we need it sandwiched in between two values or separated to two different inequalities looking at the extremes of the number line. And we really don't need to know whether in this case it's an and in this case it's an or. All of that comes out in testing the different regions of the number line. Let's go ahead and take a look at example 4, and I'm kind of already giving you a hint that this is a special case. So I've got absolute value of 2x plus 9 plus 11 is greater than 5. Let me move that 11, again always in my method trying to isolate that absolute value, and 5 minus 11 is negative 6. And then we could continue on and set up our two equations, 2x plus 9 equals negative 6, and 2x plus 9 equals positive 6, and go from there and test on the number line. But I already hinted that this is a special case. Now, why is it a special case? It's a special case because we have an absolute value that's isolated, and we're trying to decide, can an absolute value be larger than a negative number? Well, an absolute value, the lowest it can be is 0, and then it can be any positive number after that. Because we know absolute value means distance, it's never going to be negative. So can a number that's an absolute value, meaning 0 or positive, be bigger than a negative number? And that is true. Yes, it's always going to be bigger. Even 0 is bigger than a negative number. And a positive number is definitely bigger than a negative number. So in this case, yes, that will always be true. And so our answer is all real numbers. So we could use that using the real number symbol, or in interval notation, it would be negative infinity to infinity. So because I noticed this was a special case where we had an absolute value we were comparing with a negative, then I could kind of think through the process of whether it was true or not true. And in this case, an absolute value is always greater than a negative. Let's take a look at example 5. So again, I'm kind of hinting that we've got a special case. So we've got absolute value of 4x minus 3 minus 2 is less than negative 8. I'm going to add 2 to both sides. And absolute value of 4x minus 3 is less than negative 6. So in this case, again, it's a special case because you have an absolute value that's isolated. So again, the lowest the left value is going to be is 0, but it could also be any value larger than that. And then we're trying to decide if the absolute value can be less than a negative number. So remember, an absolute value can be, the lowest it can be is 0. And is that smaller than a negative number? And the answer in this case is no, never. An absolute value, no matter what you try, is never going to be smaller than a negative number. So in this case, our answer is no solution. There's nothing on that number line that will make this inequality true. So we could go through and use case 1 and case 2 and test the regions of the number line, but you would end up finding out that it would say no, no, no. And that would help tip you off that it was a special case and that there's no solution. Let's take a look at example 6. Write down that m is no less than 9 units from 5 using an absolute value. So what we're trying to say is m is no less than 9 units from 5. How we could say that is the distance from, or between, I guess I'll write between m and 5, is, when it says, where to go, no less than 9, it means it could equal 9, or it could be bigger than 9. So sometimes it's nice to just rearrange it in more of how we think. So m is no less than 9 units from 5. So the distance from m to 5 has to be bigger than or equal to 9. So the distance between m and 5 is the absolute value of the difference from m to 5, and we know that has to be greater than or equal to 9. Let's take a look at the next one. Write that p is within 0.2 units, 0.2 of a unit, of 5.8 using an absolute value inequality. So again, we can try to rewrite this. The distance from p to 5.8 and then we want to decide it's within 0.2 units. So that means it's got to be less than 0.2 units. So let's go ahead and write the distance between p and 5 as p minus 5.8, but distance is always positive, so we're going to use the absolute value to force it to be positive, and that has to be less than 0.2. And now our last example, example 8. Suppose that y is equal to 5x minus 2, and we want y to be within 0.001, so 1,000th of a unit of 6. So let's rewrite this in our words. Our distance between y and 6 is less than 0.001, 1,000th. So again, our distance between y and 6 is the subtraction, that's how we find their distance, and then forcing it to be positive is our absolute value, less than 0.001, 1,000th. And then I'm going to go one more step before we solve this. I'm going to replace y with what they told us, y is 5x minus 2. And then I'm going to start to simplify and solve. So here we have absolute value of 5x minus 8 is less than 0.001. And we could use this using a sandwiching between negative 0.001 and positive, or we can solve it like we were talking about earlier, creating our two equations. Case 1 where no changes to each side, and case 2 where we're going to multiply one of the sides by negative 1 and solve. Let me add 8 to each side here. So I get 5x equals 8.001. And then dividing by 5, it simplifies into be 1.6002. So 1 and 6,002 10,000ths. Looking over here, notice that when we're adding 8, now we have opposite signs. So we have 5x equals 7.999. And dividing by 5, we end up with x equals 1.5998, 5,998 10,000ths. And again, we want to check this on the number line. So I'm going to put those two important numbers. Here's 1.5998. Here's 1.6002. And we can test the left, the middle, and the right. So over here on the left, let's test x equals 0. In the middle, let's test x equals 1.6. And over here on the right, let's test x equals 2. Looking at, let me go ahead and write down what we had before. We had absolute value of 5x minus 8 is less than 0.001, just to kind of remind us of that inequality we started with. So let me sub in 0. Absolute value of 5 times 0 minus 8 is less than 0.001. So 0 minus 8 is absolute value of negative 8. And is 8 less than 0.001? No, we're not going to shade in there. Let's test with 1.6. Absolute value of 5 times 1.6 minus 8 is less than 0.001. 5 times 1.6, we can kind of think through 5 times 1 is 5. 5 times 0.6 would be 3, so that ends up giving us 8 total. And 8 minus 8 is 0. And absolute value of 0 stays a 0. And so yes, we definitely want to shade in the middle there. And now we can test something larger like 2. 5 times 2 minus 8 in absolute values. So 10 minus 8 is 2, and the absolute value of 2 stays a 2. And so definitely no, 2 is not less than 1/10,000th. Oh, excuse me, 1,000th. And so our answer is going to be between 1.5998 and 1.6002. Because there's no equal sign, again, we're going to use parentheses or open circles. So our final answer is going to be 1.5998, 1 in 5,998 10,000ths, all the way to 1.6002, 1 and 6,002 10,000ths. And that ends example 8.